So to finish the quantum numbers, the magnetic quantum number M is symbolized by the letter M, represents the number and orientation of orbitals in space. So it's basically how the orbitals are arranged in 3D space. And generally when we look at the orientation, we're going to consider things, for instance, around an X, Y, and Z axis system. It defines the number of electrons per orbital also, and any orbital regardless of type, and we have multiple types, but every individual orbital can hold a maximum of 2 electrons. They may have more. And now we're going to list the energy levels, sublevels, and number of orbitals and electrons. Okay, first with s orbitals. S orbitals, as the image here shows, are spherical. There's always one of them per s sublevel. And s sublevels as well as s orbitals are found on all energy levels. So when we look at this, we've got the nucleus here in the center. We've got an axis system here, here, and here, and of course with the sphere, the outer boundary of the sphere is going to be equidistant from the center of the sphere in the nucleus. And what we would say is that the electron wave has approximately a 90% chance of showing up on the surface of this sphere. So this is what's known as a probability surface, and we would say that everywhere on the surface of this sphere in 3 dimensions has an equal chance of finding an electron, and that the chance is normally set when doing the calculation at 90%. P orbitals are always found in P sublevels. There are always 3 P orbitals per P sublevel. P sublevels are found on energy level 2 and higher. And as you can see from the arrangement here, we have a sort of a dumbbell-shaped orbital. This particular one is arranged on the x-axis. We call it P subscript x. This one is arranged on the y-axis. We call this the py orbital. And on our third one, we have one arranged along the z-axis, which we would call pz. So we have one arranged on each axis in a 3-dimensional axis system. Again, each of these holds 2 electrons. So if we go back to this holds two electrons, and since we have one of them on an s sublevel, we're always going to have 2 electrons in every s sublevel and s orbital. On a p sublevel, we have up to 3 p orbitals, and each of these holds 2 electrons. So this can hold 2, this can hold 2, and this can hold 2. So when we look at the total p sublevel, this would represent the sublevel, and we've got 2 in each dimension. That's up to 6 electrons that we can hold, or 2 times the number of orbitals, because each orbital, we've got 3 of them, each one of them can hold up to 2. 2 times 3 is 6. D orbitals are found in D sublevels, and we actually will have 1, 2, 3, 4, 5 D orbitals per D sublevel. Okay, So with each of these holding 2 electrons, and that means the entire sublevel, which would be represented by all of the orbitals thrown together into one big bundle, so it would have a total of 2 times 5, 10 electrons. These are found on energy level 3 and higher. No d sublevels or d orbitals in energy levels 1 and 2. And we have f orbitals. We've got 1, 2, 3, 4, 5, 6, 7. So there are 7 d orbitals. I'm sorry, f, my mistake. F orbitals per f sublevel. And again, since all of them hold 2, then the entire f sublevel holds up to 14 electrons. So 2 times 4, 2 times 7, 14 electrons. These are found in energy level 4 and higher. So to summarize the magnetic quantum number, we're going to look at and actually to summarize the 3 quantum numbers thus far, we're going to look at the energy level, the sublevel, the orbitals, and the number of electrons. So for energy level 1, we have only one sublevel, which is called an s sublevel. In that one s sublevel, we have one s orbital. And that one s orbital, since we only have one and every orbital holds 2 electrons, that orbital holds 2 electrons, total electrons, 2. So all of the electrons on the first energy level are in an s orbital inside of an s sublevel inside of the first energy level. Energy level 2, we have 2 sublevels. We have the 2s sublevel and the 2p sublevel. The 2s sublevel has one s orbital, which holds 2 electrons, and 2p has 3 p orbitals, which holds a total of 2 times 3 or 6 electrons. That gives a total for the second energy level of 6 plus 2, 8 electrons. And also remember that 2 times n squared, which gives the total number of electrons on an energy level. If we're on energy level 2, then 2 squared is 4 times 2 is 8 electrons. Let's change ink color. Okay, on energy level 3, we have 3 sublevels, 3s, 3p, and 3d. In 3s, we have one s orbital. Notice that every time we have an s, we only have one of them. And that one s orbital holds a total of 2 electrons. We have 3 p orbitals, which hold a total of 6 electrons. And we have, for D, we have a total of 5 d orbitals, which would be 10 electrons. That gives a total of 18 electrons, or 2 times n squared again, where n is 3. 3 squared is 9, times 2 is 18. And then the fourth energy level I'll try to squeeze in. The fourth energy level, change ink so it's maybe a little easier to keep up with. Fourth energy level has 4s, 4p, 4d, and 4f. 4s has one s orbital, which is going to hold 2 electrons. 4p has 3 p orbitals, which is going to hold 6 electrons. 4d has 5 d orbitals, which holds 10 electrons. And 4f has 7 f orbitals, which holds 14 electrons. So that's 14 plus 10 would be 24, plus 6 would be 30, plus 2 more, 32 electrons, or 2n squared, where n is 4, 4 squared is 16, times 2 is 32. Now, it's important to know this information. It's important to know that when you're on an s sublevel, how many orbitals are there? When you're on a p sublevel, that you've got 3 p orbitals and so forth, to be able to do something called electron configuration that's coming up soon. Okay, our last of the 4 quantum numbers is the spin quantum number, represented by the letter S, proposed by a physicist by the name Wolfgang Pauli. And what Pauli found that this 4th quantum number, which was not provided by Schrodinger but by Pauli, indicates what an electron does while it's inside of an orbital, which is spin. It's either going to spin clockwise, which has a numerical value of plus 1/2, or counterclockwise, which is negative 1/2. And that leads us to the Pauli exclusion principle, which states that no 2 electrons in an atom may have the same set of 4 quantum numbers. Every electron has a unique set of quantum numbers. So in the last slide of this particular presentation, we're going to look at an analogy that might help you understand what quantum numbers are actually looking at. What quantum numbers do, in a sense, is allow you to zoom in from a large scale to a small scale. As we go from large scale to small scale, we're going from, the large scale would be, for instance, going from energy level to orbital, with sublevel in between. So large to small scale, it's like you're zooming in on what the electron's doing. And then when we get out here to the orbital, we actually can see what the electron's doing in the orbital, which would be spinning. And this is difficult to talk about, but we'll just say spinning on an axis. Okay, so for instance, let's suppose you're looking at a school, maybe a 2-story building. It doesn't have to be a school, just a 2-story building from a distance. Okay, as you look at it from a distance, you can see the outline of the building. You may be able to see that it's color, but you probably can't tell what it's made of. Maybe you're 400 or 500 yards away, and so you can see it, but you can't see the details of the construction. That's sort of looking at like the energy level. We can stand back at the atom and look at it, but it's actually probably beyond the energy level atom. We're probably outside the energy level and maybe looking at the atom level. So we're looking at the whole atom from a distance, and we're seeing basically the electron cloud. Would be like looking at a building from a distance. We then come closer, get closer and closer and closer, and we get some more detailed structure. And we realize that our building is maybe broken down into floors. And let's say 3 floors. So it's a 3-story building. And we then go inside the building, and we see that on each floor we have rooms. And these rooms are, of course, analogous to sublevels. So we're going from building to stories on a building that we can see the details and how many floors there are. Then on each floor we have rooms, and within the rooms we have chairs, and within the chairs we have people doing something, sitting. So this is very similar. We start out at a large scale. We can see an atom at a distance, which look like a fuzzy blob, a cloud. We then zoom in closer, and we can see that that cloud is actually broken into energy spaces. And within those energy spaces, we have subspaces that are smaller, such as rooms rooms on a floor of a building. And then within the sublevel, we have other regions of space that can be occupied by electrons, such as orbitals, just like we have rooms, and in rooms we have chairs that can be occupied by people. And then finally we can see what the electrons are doing, just like we could see if we came in close enough, we could see what people were doing, which is sitting in the chairs. I hope that helps explain a little bit about what we're looking at with this. It's a very detailed look at electrons. It's very unique, each electron getting its own unique attention in terms of being assigned basically an address, or from where it is on which floor it's on to what it's doing when it's sitting in its chair, so to speak, which is spinning. We can then use these quantum numbers to help us do something that allows us to produce some sort of map of what the electrons, how the electrons are arranged in the electron cloud. And that will be the subject of the next video.